Hello and welcome to this video. In today's video, I am going to introduce the function odeint, which is in the module syspy.integrate. This function is used to solve differential equations of the form dy by dt equals to some functions in terms of y and t. And from this definition, you can see that odeint actually solve first order differential equation, where y is the dependent variable and t is the independent variable and f is the function. Now, to be able to use this, we have to define in Python a model called ODE, let's say, and it will take some variables y and t. And within the model, I will define the differential equation as dy dt equals, in this case, for first example, let's say minus 2 times y. Now, to do that, I need to create a time array, and I can define the starting point and the end point. And I need to say I will have, let's say, 50 or 100 samples representing the time array between the starting and the end point. Then I will call the function and I will assign it to some solution, and I will pass to it the model and the initial parameters plus the actual time array. Because in differential equations, when we try to look at the behavior of the differential equation, we need to define the time window in which this function is actually operating and look and try to understand the behavior of the differential equation. So let's not waste any time and just jump into a Jupyter notebook where I can actually start showing you how to do this. Now, what I am going to do, I am going to split the code into different cells because it's much easier for you to actually diagnose errors when you have the code split into cells. And each cell will contain a complete functionality, if you like. Now, in the first cell, I will import the libraries that I need, and the libraries which are required are NumPy, which I am actually importing as a short name MP. And then I need from syspy.integrate the model, I need the function odeint. Excuse me. And then I imported matplotlib.pyplt as PLT. These are the three models or methods or functions that I need to use in this case. The two libraries plus this function odeint. Now, as I said earlier, we need to define the model which actually simulate the differential equation. And in this case, I call it model, and I use the keyword def to define, and then I said that model will take two arguments, y and t, and within the model, I simulated the differential equation, and it's a decaying differential equation where it's actually dy by dt is equal to a minus constant multiplied by some y. And then the function will return dy by dt. However, notice here that to define dy by dt, we don't use the actual dy over dt. It's dy followed by dt straight. Then I initialize the initial variables, and in our case is just y, and as you can see is defined as 1 because it needs to start at some value and decay all the way down. Then I created a time array, and I used the function linspace to define the array. I called it through NumPy, and I said the starting point is 0, the final point is 5, and I need 100 sample between 0 and 5, i.e. there will be about 20 points between 0 and 1, and 20 points between 1 and 2, and so on. Then I actually called the model and assigned it to variables called solution, and I passed to the model to this function odeint. I passed it the model, I passed it the initial y, and I passed it the time array. Then I plotted the solution by passing to this function plot, which I called it from matplotlib. I passed to it the time array, and I passed to it the solution. Then I use the method xLabel to define the xLabel, and I use the method ylabel to define ylabel. And then I called the title method to actually give a name to our plot, and then I use the method show to show the plot in my Jupyter notebook, because without this probably you will not be able to actually show it, and in that case you will need to have another statement, which is percentage matplotlib space inline, and that way the Jupyter notebook will understand that the plotting can be showed within Jupyter notebook. So let's see how this actually plays for us. I'm going to run the first cell to import all these libraries. Then I will define the function. Then I will set the initial variables, then create the array, then start the solution by calling the function odeint, and then I will actually plot the solution. And as you can see, I started with y initially at 0 at 1, and it decayed near enough to 0 around 5, and it should have about 20 points between 0 and 1, and so on. So as you can see, in this case, what I did, I split the code into cells, and each cell is actually, it's like a step for us, where I imported the libraries, I defined the model, I initialized the initial parameters, then I created the time array, then I called the function odeint, and I solved the equation, and then I plotted my solution. And in all the examples I will be using in this video, I will be doing exactly the same regardless of the equation I am trying to solve. Now, the actual model or the solution might be different because of the number of arguments and the number of parameters that we already have, but the solutions follows exactly the same way. And when we come to solving second order differential equations, whether it's just a representative differential equation, or we are looking at a system and looking at the dynamic equation for that system, and we are trying to solve and try and look at the behavior of that system, we will actually follow the same steps. So let's look at the second example. And in the second example, I used a variable k in my equations instead of 2, because it's dy by dt is equal to minus k multiplied by y, and k in the first example was 2. In this case is actually k, a variable, which means I have to define this in my code. So again, as you can see, I started with importing the libraries, then I defined the model, and notice that the model now take an extra variable, which is k, and this k is something which I have to define when I define my variables, and I define dy by dt to equal minus k multiplied by y, and I retain dy by dt. And then I initialized my condition y0 and k value, and you can see I defined the k to equal 0.2 in this case. And then I actually went further and used NumPy and the function linspace to create the array between 0 and 5 with 100 samples in it. Then I called the function odeint, and I assigned it to a variable called solution, and in this case I passed it the model, the y, the t, and I passed some argument here because I have an extra argument that I need to pass, which is the k value. Then I plotted my results, and let's see how that is different from the first example. I imported the libraries, defined the model, initialize the conditions, create the array, solve the equation, and then plot. And as you can see, I get exactly the same plot with the difference rather than y being equal to some value. Now I actually use k to equal 0.2 instead of 1, and I multiply it by y, which is 1, and we decay in that manner. Okay, now we can actually simulate for systems, and I'm looking at the logistic growth, and in this case I am actually looking at two extra variables, which are the growth rate and the carrying capacity of whatever trucks that we are using to ship some goods. Okay, so the first thing, in this example I didn't import the libraries for a simple reason that I have already imported them in a previous cell within this notebook. And it's just to show you that if it's already in this notebook, I don't need to import it again. So in my first cell here, I started with creating the model, and the model now take two extra variables, r and k, plus the y and t, and then I defined my dy by dt as it is here, and then I needed this function to return dy by dt. Then when you see now, it's not just y I am actually defining, I am actually defining the two extra parameters, which are r and k. So I defined y to equal 0.1, I defined r to equal 0.1, and I defined k to equals 1. Then again, in the same manner as before, I created my time array, and then I called odeint to solve this equation, and I passed to it the model, starting y, the t, and then I actually pass to it the argument. In this case, it's 2 arguments. Then I plotted the solution. So let's see, as I said again before, I didn't import the libraries in this case because they have already been imported. So when I run these, they should run without a problem. So I created the model, I set the initial condition, create the time time array, and then I actually solve the equation and then plot the results. And as you can see, it actually plots. Now, if you start playing with these values here, you will see that this solution changes. Therefore, I advise you to play so you can see how these values affect the performance of the or the dynamics of the system itself. In the next example, I am actually trying to introduce the function sine into the differential equation, because I know that NumPy already have these as functions within NumPy, which is sine, cosine, tan, and so on. Therefore, I want to solve a differential equation of the first order, which says dy by dt is equal to 5t multiplied by sine 2t. So I imported the libraries in this example. Then I created the function, and I can see I only need to pass two variables, y and t. And then in the function itself, I call the function sine from NumPy to simulate the sine functionality for me, which is actually sine 2t, and I multiplied it by 5t, which is equivalent to the equation as it is defined here. And then I returned dy by dt. Then I initialized y, then created the time array, then did the solution and plotted. So let's see if this actually works as I expect it will. And as you can see, it actually works, and we have this. This is not really a full sine as you know it, because it's actually multiplied by 5t, and and therefore it actually changes depending on the value of 5 times t. T is the actual time value which we take in, and 5 is just a constant, and all that the result of that is multiplied by sine t. So change these values and see how the actual dynamics changes. In the next example, I am trying to show you how we can solve second order differential equation. And I said that odeint only solve first order differential equation. Therefore, I need to simulate the second order differential equation as a first order differential equation and then solve my differential equation. However, my model now supposed to actually solve the two first order differential equations. The first is the dy by dt, and the second is dz by dt, where I said the variable z is equivalent to dy by dt, and then I will be able to see that d squared y by dt squared can actually be simulated as dz by dt, which is the first differential of z will give us the second differential of dy by dt. Then I set my equation by taking the left-hand side, keeping just dz by dt, and taking the rest to the right-hand side. So I started by importing the libraries, then I actually created the model. And in this case, as you can see, I have an equation for dy by dt, and I said it's actually going to be the first index of y, because I'm actually going to create some array which contains two values for y. The first is actually the initial and the value, and the second is actually the value of dy by dt, where I will store them there, and then later I will call them to myself to extract the solution. So, and then I said dz by dt, and this is the same as the equation which is defined here, and this is dy by dt, and I said that z is actually going to be at the first position, first index within this array. Therefore, now I actually will run this, and then run the second cell, and then create or initialize the array of the initial values. And then I created the time array in exactly the same manner, just starting point, end point, and the number of samples. And then I called odeint to solve the equation, and I passed to it the model plus the two variables. And then I extracted the solution by saying y is equals to index 0 and z is equals to index 1, and that's what I have actually put there. And then I plotted my solution. So let's see if we can actually achieve the result as we said. And as you can see now, I have a plot which contains two different results. And for that, I used a legend to differentiate between the two. And I said that the blue is yt and the orange is dy by dt. And that's why I actually, when I plot ty and I plot tz, and I said that the label is yt and the label is dy by dt, and these are the arguments which are going to be taken by the legend. And it actually finds, in this case, if I don't specify where this legend is going to be, it finds the best location for the legend, and it actually put it in that location. So this is a nice way of actually simulating and differentiating between the results of two functions. Okay. Next, I want to actually simulate a differential equations for a pendulum. And I know that from your physics lectures, you've actually studied pendulum and you derived the equations for a pendulum. Therefore, I'm not going through the derivation of the dynamical equation for the pendulum. I'm just going to state it as it is, which is d squared theta by dt squared is equal to gravity over the length of the pendulum multiplied by sine of theta minus b which is the damping coefficient multiplied by d theta by dt, plus A, which is the external force multiplied by sine omega t, where omega is the frequency of the external force. And then I said that dx by dt is equal to L d theta by dt, and I have changed the actual two second order differential equation into a first order differential equation to be able to simulate it. So let's see how I achieved this. I imported the libraries, then I defined the function. And here is what actually different from the previous examples, where I am actually changing the name of the function, and then notice what I am passing. I'm passing y and t, and then I have a number of arguments that I am passing, g, l, b, a, and omega. Within the model, I have defined two variables here, theta and omega, plus the x, and I assign them to y. Then I actually put my differential equation, which is dy by dt, which is given here. And I said this is it's equal to omega, and it's minus g over L multiplied by sine of t, minus b multiplied by omega theta, plus a multiplied by sine of omega t, and I pass L multiplied by omega theta, and I return dy by dt. The parameters I needed to define are the gravity, the length of the pendulum, the damping coefficient, the actual external force, and the frequency of the external force. Then I needed to set the initial conditions, and notice that theta is actually pi over 4, and omega theta is 0, the initial angular velocity, and then the horizontal displacement in this case is going to be 0, and then y, it actually has theta 0, omega, and theta 0, and x 0. So I'm passing this as an array. Then I created the time array, and it starts at 0 and ends at 10, and I have 1000 samples between 0 and 10. Then I solve the equation by calling the function odeint, and then I actually call the model, pass the model, sorry, pass y, the initial y, which is given to us here. Okay, then the time array, then the extra argument, which is g, l, b, a, and omega, which are these extra variables which are here. Can you see I have 2, 4, 5, I have 2, 4, 5, passing them as arguments to this function odeint. Once I have actually solved it, then I need to extract the values. And in this case, I have here three values, theta, 0, omega, and theta plus x. But I am actually looking at index 0, index 1, and index 2, or at everything after index 0. I use slicing in this case. And once I have actually extracted, then I can use subplot to plot two figures for me. And as you can see, when I called subplot function, and I gave it the name or the number 121, when I called it again for another subplot, I gave it a number 121. Now, I create these two subplots under the same figure size, which is figure, and in there I pass the figure size, which is equal 10 by 5. And then within the subplot, I called the function plot, and I pass this t, theta label, and the label is angular displacement. Then I created my x and y labels, and I put a legend so I know what is actually there going to be, which is that label. It should take it, and it tells me that this color is for this function. Then in subplot 2, I actually again call the plot, and I pass to it the argument, and I use X and Y labels to put the names of the X and Y sides, and then I called for legend, and then in this case I used the function tight underscore layout, and this will actually give me the best fit of the space for the two figures, because with two figures it's not too bad, but if we are using more figures we need to actually leave a space between the figures on the left and on the right and the top and the bottom. Therefore we can lay them out as good as we can. So let's see how this will actually work for us, because it's a little bit more complicated, because we are simulated a more, how shall I say, a more sophisticated equation than what we have seen in the previous example. So I run the import of the libraries, then I define the model, then I initialize the parameters, then I initialize the conditions, and then I will actually create the array, the time array, and then I will try and solve the equation by using the function odeint, and then I will need to extract the solutions, and once I extracted the solution, then I can actually plot them. As you can see in this case, I should have two subplots. I have a legend, and I have the two subplots, and in the legend it tells me that it's angular displacement and it's horizontal displacement. And as you can see, using this tight has actually made utilize the whole space which is here. Now if I remove or stop this statement tight underscore layout and I run this again, you can see it actually gives me, but the plots are smaller. I didn't utilize the whole space, and it's fine when you have two small plots like this, but if you have more plots, you want to actually utilize the space the most efficient way you want, and that tight layout will actually help you to do that, because it will do it automatically for you. Next, I want to show you how we can actually solve a second order differential equation. And in this second order differential equation, we have which is actually for it has a mass multiplied by some weight, and the weight is actually attached to a spring. So it's actually a spring mass system simulation, which simulate the suspension of a car. So the mass will be the actually car mass, and it's actually multiplied by d squared x by dt squared plus c, which is the damping coefficient of the spring, multiplied by dx by dt, plus k, which is the spring constant, and multiplied by x, and x is the displacement of the system, because when you attach the spring, a mass to a spring, the mass will cause the springs to be displayed by a small amount. Now, if you leave that at it will stop at what we call equilibrium state, and we call that equilibrium at zero. Now, if I disturb the mass up or down, it should start to oscillate, and it will oscillate up and down until it actually go back to equilibrium. And the displacement above is negative displacement, and displacement below is positive displacement, and that's part of the dynamics. I don't want to enter into that, because you should actually have seen this in your lectures or in some information about the derivation of the equations. I'm here to show you how to solve it using Python. I don't want to go into the dynamics of the system and how we extract this equation. And then I took this equation and I actually simulated it in my Python. I started by importing the libraries, then creating the model, which is car suspension. Again, can you see I passed Y and T, and then I passed mass, C, K, and F, which are force, spring constant, damping coefficient, and mass. And these needs to be passed as argument later on to the model. And then you can see I said that X and V, and I assigned them to Y. And then I said dy by dt is V f of t minus C multiplied by V minus K multiplied by X, and all that is over M because my equation actually have an M multiplied by that. So I divided by M and I took these terms to the other side. And then I initialized my condition, which is the mass, the damping coefficient, and the spring constant. Then I created another function, which is external forces. And I said the external forces are actually this 5,000 multiplied by sine function of 2 multiplied by pi multiplied by 1 multiplied by t. And t, of course, is the time array. And then I initialized my conditions, and I have 3 x0, v0, and y. And y in this case is actually two variables, which are x, initial x, and v, and in terms of an array. And once I've done that, I'll create the time array. And as you can see, between 0 and 10, it's 1,000 samples. Then I actually called my function odeint, and I passed to it the model, yt, y, and t, and then I pass to it the argument, which is the 5 arguments which are present in our model at the beginning. Then I extracted the solution for x and v, which are here, x and v, which are important at index 0 and index 1. And then I actually use subplot to plot the displacement and the velocity. So let's see how this actually works. Now this is optional, you run or you don't run because we are working in the same Jupyter notebook. Now let's see, the function is created. I set the parameters. I define external forces function, and then I set the initial conditions, and then create the time series, then carry out the solution, extract the actual values, and then just run matplotlib to plot the figures. And as you can see, now I have two plots, one for displacement, one for velocity. And if I compare these two, you can see they are different, even though at the first instant you think they are similar, but they are different. Okay, if you look, for example, at this area here, it's actually different from this area here, with a little bit of actual shift on the time series. So if you actually compare it all together, then you can also use one plot, by the way, instead of using two plots, and plot them both together in here and give them different colors, and then you will be able to actually look at time instant and the behavior of the velocity and the displacement and so on. So it's actually a nice way of visualizing and comparison of different functions for the same dynamic system. Next, I want to actually simulate the solution for an electric motor. And in this electric motor, I have actually extracted the equations for both the motor and the electric circuit which represent the motor, and then I looked at the commonality between them, and accordingly, I achieve these equations. And the equation says V of t is actually equal to the drop due to t plus the drop due to the inductance plus the EMF. And then dW by dt is equivalent to the torque due to mass and to the damping coefficient due to the frequency of the torque and so on. So I actually defined what are the variables here, and then I started simulating, started by importing the libraries. Then the most important is the model. I call it DC motor, and as you can see, the first two variables are always in my model, they are passed, and then I have extra argument, which is which is R, L, K, EMF, and J, B, Vn, and the load torque. Then I defined y to equals, assigned I and omega into y, and then I said dy underscore dt is actually equal to Vn minus R times I minus Ke times omega, all of this over L. And then I said d omega underscore dt, which is rate of change of omega by dt, is equal to load torque minus b times omega over j. And then I returned this array, which is the rate of change of I with t and the rate of change of omega with dt. Then I set the parameters to the values you can see R2, L 0.5, EMF is actually 0.01, J is 0.02, and B is 0.1, and Vn, which is the voltage, is 5 volt, and the torque is 0.1. And you can see I have the units assigned, so you know what units they are. And then I initialized the conditions and then created the array for the time in which I want to check the dynamics of the system. Then I called the function odeint, and I passed to it the model and the y and t, and then the argument, which are the rest of the parameters which are in the function. And then I actually, once I've solved it, I extracted the solution, which is for the current and the angular velocity, and then plotted the result for both the current and the angular velocity. Let's try and run this. So if I run this, model is created, I initialize the values, set initial conditions, and then do the solution, extract the variables, and then plot the results. And as you can see now, I have plotted the dynamics and I can look at the actual behavior of the system that I am trying to solve. As you can see, odeint is a very good model which is available within Python, and you can use it to solve first order differential equation. And I showed you in this video how we can actually define a second order differential equation as a first order differential equation, and then how we can actually use odeint to solve. Now, odeint is not the only model that actually solves differential equations. There is others. Please try and check these other models that solve differential equations. And once you actually found it, then use this code as a starting point and replace the model for solving this differential equations or the function that solve this differential equation from this new library into this code, and try and verify that you can also understand how to use other libraries to solve differential equations. I will stop this video here. I thank you for watching the video, and I hope to see you in the next video. Thank you and goodbye.